In this packet, we want to discuss the mean value theorem. But first, we will look at Rolle's theorem. Rolle's theorem states that if a function is 1 continuous on the closed interval a to b, 2 differentiable on the open interval from a to b, and f of a being equal to f of b, then there is a value c in ab such that f prime of c is 0. Some examples. This example is a horizontal line on a to b, which just means f prime of c equals 0 for any c between a and b. Remember, the slope of any horizontal line is 0. In this example, we see that the function is 1 continuous on a to b and 2 differentiable on a to b. And f of a is equal to f of b, which means there is a c in between a and b such that the derivative at a value c will be 0. We can actually see this in the picture 2 by following the curve to its horizontal tangent line. Another example that is similar to the previous example. We see the curve is continuous on a to b, differentiable on a to b, f of a is equal to f of b, and clearly we see a value c where f prime of c is 0. In this example, we again see that the curve is continuous on a to b, differentiable on a to b, f of a equals f of b, and we can actually see that there are 2 places where the derivative of the function is 0. Note, if f of a equals b, f of b, and fails to be continuous on a to b, or fails to be differentiable on a to b, we cannot guarantee the existence of a point c on a to b where f prime of c is 0. A few of these types of examples are listed below. Now let's look at an example using Rolle's theorem. First, since this is a polynomial function, it is definitely continuous on the closed interval from 0 to 1. Second, since it's polynomial, we know it's differentiable on the open interval from 0 to 1 as well. Third, we plug in endpoints to show that f of 0 equals f of 1, which equals 0. So, by Rolle's theorem, we know there exists a c between 0 and 1 such that f prime of c is 0. Now, let's find that c value. We get c equals 1/3 or c equals 1. But remember, it has to be on the open interval from 0 to 1, so we don't include c equals 1. Here's a brief sketch of the graph. Find f of 1/3 real quick. And voila, a sketch of what the graph looks like from 0 to 1. This example is a quick one since tan of theta is undefined at x equals pi over 2. A quick peek at what the graph looks like on the interval 0 to pi. Now we look at an example that uses the intermediate value theorem along with Rolle's theorem. We want to show that there is exactly one real root for this equation. So first we plug in -1 and 1 into the function. We see that f of -1 is less than 0. And f of 1 is greater than 0, which means there has to be an x value that will give 0 for our equation between -1 to 1 by the IVT. Now we use Rolle's theorem to show that there is exactly one root. Since the function is a polynomial, we know it's continuous on -1 to 1, as well as differentiable on -1 to 1. So let's say there exists f of a being equal to 0, which equals f of b. Then there is a c such that f prime of c is 0. But f prime of x is equal to 3x squared plus 1, which is always positive. Therefore, there exists only one real root between -1 and 1. Now we look at the mean value theorem. The mean value theorem states that if 1, f is continuous on the closed interval a to b, and 2, f is differentiable on the open interval a to b, then there is a c in a to b such that f prime of c equals f of b minus f of a over b minus a. This is actually pretty easy to understand with a picture. First, we select an interval, a to b, and draw the secant line. Now, just move that secant line up until you have a tangent line, which is, of course, f prime of c. An example. We know this curve is continuous on 4 to 8 since it's just a root function. Now we need to verify that it is differentiable on the open interval from 4 to 8, which it is. So the mean value theorem says there exists a c in 4 to 8 such that f prime of c equals f of 8 minus f of 4 over 8 minus 4. So we set the derivative of our function equal to that and solve for c. and we end up with c equals 5. And here is a sketch of what this looks like. Example B, we see that the function is continuous on -1 to 8. After taking the derivative to see if it is differentiable on the open interval from -1 to 8, we see that t cannot be 0, which means h of t is not differentiable at t equals 0. And this means we cannot use the mean value theorem here.